Question number 1. Find the exact value of the integral from 1 to 2 of ln 3x dx. Give your answer in the form a plus ln b, where a and b are integers. So, if you want to integrate ln, we always do this by parts. So we're going to take this as a product of 1 multiplying the ln 3x. And so we need to figure out what u is, and we need to figure out what dv is. So for that we use late, where L is your logarithms, A is algebra, so things like x, x squared, x plus 3, T is trig, E is your exponential functions. Okay, so whatever is higher up on the list, that's what you pick as your u. In this case, 1 would fall under algebra, and then our ln would fall under logarithms, so we pick our logarithm to be u. So u is ln 3x, and so dv dx has to be 1. So we need to find du dx. So to differentiate ln, it's 1 over the bracket, so 3x, multiplied by the derivative of what's inside the bracket. So differentiate the 3x, you get a 3. And I hope you can see that the 3's cancel out, and we end up with 1 over x. And then we need to find v, so we need to integrate dv dx. If you integrate 1, you're going to get simply x. And so using the formula for integration by parts, which is in the M of 19, we can say that for now I'll ignore the limits. The integral of ln 3x dx is equal to uv. Our u is the ln 3x, our v is the x. So x ln 3x minus the integral of v du. So v du, that's x, times the 1 over x, and this is with respect to x. So that's the integral of ln 3x dx is equal to, this is x ln 3x minus the integral, the x and the x cancel, and we just end up with 1. So we need to integrate 1. So the integral of ln 3x with respect to x is equal to x ln 3x minus, if you integrate 1, you just get x plus a constant of integration. And now we can bring in back our limits. So we know that if we integrate ln 3x, we're going to get x ln 3x minus x, and we wanted to evaluate this from 1 to 2. So you can start with the upper limit, so that's going to be 2 ln 3 times 2 minus 2, and now do the lower limit, so that's 1 ln 3 times 1 minus the 1. Okay, so if we simplify this, that is 2 ln 6 minus the 2, and then I've got minus the bracket, so minus this here becomes ln 3, and then minus 1, so plus 1. Do they specify what they want? They say they want the form a ln b. So what we can do here is bring the power up on the 2 ln 6. We know that if I have a ln b, we can use a ln b. This is the same as ln b to the a, so I can bring up the a and it becomes a power. So that's what we want to do, so that it becomes ln 6 squared. Then I've got minus 2 plus 1, which is just minus 1. Then I've got the minus ln 3. So here I've got ln 36 minus the ln 3 minus the 1, and I also have a law of logarithms that says if I've got ln a minus ln b, this becomes ln a over b. So I can use that and say that this is ln 36 over 3 minus 1, and so that becomes 36 over 3 is 12, so ln 12 minus 1, or in the form that they wanted it, which is a plus ln b minus 1 plus ln 12. And that is the final answer. Question number 2, part A. Show that the equation log to the base 4 of 2x plus 1 is equal to 2 log to the base 4 of 3x minus 1 minus 2 can be written as a quadratic equation in x. 3 marks. Okay. So I've got log to the base 4 of your 2x plus 1, and this is equal to 2 log to the base 4 of 3x minus 1 minus 2. So what you want to do as a first step is you want to put all the logarithms on one side. So I'm going to have log to the base 4 of my 2x plus 1 minus 2 log to the base 4 of 3x minus 1, and this is all equal to negative 2. And we're going to use a law of logarithms that we used above, which was this one, because the idea is I eventually want to combine my logarithms together, but I want to use this to raise this 2 up. So that becomes log to the base 4 of your 2x plus 1 minus log to the base 4, and this is now your 3x minus 1 squared. Okay, this is equal to negative 2. And then we're going to again use the same law of logarithms we used there. To simplify here, we want to combine the two logarithms into one. So that becomes log to the base 4 of your 2x plus 1 being divided by 3x minus 1 squared. And this is equal to negative 2. So to get rid of log to the base 4, you have to use its inverse function. The inverses of your logarithms are the exponential functions. So since we have log to the base 4, the corresponding exponential function is the one with the base 4. So I have to do 4 to the power of log, and on this side I do 4 to the power of negative 2. So this 4 will cancel out my log to the base 4, and I just end up with 2x plus 1 over 3x minus 1 squared, and this is equal to 4 to the negative 2, which is 1 over 4 squared, so 1 over 16. Okay, and now we can cross multiply. So I've got 16 times 2x plus 1 is equal to 1 times 3x minus 1 squared. Okay, and we can expand. 16 times 2x, that's 32x plus 16, and then square the 3 here, that's 9, square the x, that's x squared. 2 times 3x times negative 1, that's negative 6x, square the negative 1, that's a positive 1. And put everything on one side, so I'll move these two to the right. So I've got 9x squared minus 6x minus 32x plus the 1 minus 16, and this is equal to 0. So I've got 9x squared minus 38x minus 15 is equal to 0, which is indeed a quadratic equation. Now part B says, hence solve the equation log to the base 4 of 2x plus 1 is equal to 2 log to the base 4 of 3x minus 1 minus 2. Okay, so we've already shown that this equation can be reduced to this quadratic. So if we solve this quadratic, we have solved that equation. So let's do that. We can use the quadratic formula, and x is equal to minus b, so minus minus 38 plus or minus the square root of your negative 38 squared minus 4ac, so 4 times 9 times negative 15, and this is O being divided by 2 times a, so 2 times 9. And so x is equal to, let's punch this into the calculator, that's 38 minus the square root of negative 38 squared minus 4 times 9 times negative 15 over 2 times 9. And we've got, that is an ugly solution, 19 plus or minus 4 root 31 over 9. Those are our two solutions. Okay, I'm just going to separate them. So 19 minus 4 root 31 over 9, and 19 plus 4 root 31 over 9. So the negative one, if we write that as a decimal, is negative 0.363. So I want you to keep in mind that for logarithmic functions, they are only defined when x is positive, right? If you recall the graph of a logarithmic function, it looks something like this. This is y is equal to, in this case we'd say log to the base 4 of x. This is your y-axis, that's your x-axis. Right, they're only defined when x is greater than 0. whenever x is negative, then they're not defined. So we can't actually accept this solution because it will cause us problems when we try to punch it into that logarithm there, because it can't process that value. So we're going to disregard that solution. So therefore our solution must come from the positive. And if we punch that into the calculator and get its approximate value, this is 4.59. So we can conclude that therefore x is 4.59. And that will be our final answer. Question number 3, part A. Express 3 root 2 sine x plus 45 degrees plus cos in the form r cos x minus alpha, where r is greater than 0 and alpha is between 0 degrees and 90 degrees. So we have 3 root 2 sine x plus 45 degrees plus cos x. For us to be able to express this expression in the form r cos x minus alpha, we first need it in the form a sine x plus b cos x. Because once we get it in this form, I know that my r is just going to be the square root of a squared plus b squared, and I know my alpha is going to be arctan of a over b. So our goal is to see if we can reduce our expression into the form a sine x plus b cos x, so we can rid off a and b and just use the formulas below. So I can see that I've got a compound angle here, x plus 45 degrees, so I need to expand that compound angle. If you go to the MF19, you'll find the compound angle formula for sine. So sine a plus b is going to be sine a cos b plus cos a sine b. So that's what we're going to use. So this becomes 3 root 2, and it's going to be, I'll put a big bracket here. Our a is x and our b is 45 degrees. So I've got sine x cos 45 degrees plus cos x sine 45 degrees. And this is all being added to the cos x. So I've got 3 root 2. We can evaluate cos 45 degrees with our calculator. So let me change my calculator to degrees. Cos 45 is root 2 over 2. So that means this here becomes root 2 over 2 times the sine x. So I've got root 2 over 2 sine x. And then I want to also evaluate sine 45 degrees. If I'm not mistaken, it's the same as cos 45. Yes, it is. So this is also root 2 over 2, but it's multiplying the cos x. And we've got a cos x adding outside. Right, now let's expand. So I've got 3 root 2 multiplying my root 2 over 2, and that gives me a 3. So I've got 3 sine x, and then it's the same numbers multiplying here, so I also get a 3 cos x plus my cos x there. And so I get 3 sine x plus 4 cos x. And I hope you can see that now we have the form a sine x plus b cos x, our a being 3 and our b being 4. So I can say that r has to be the square root of 3 squared plus 4 squared, which is what? 9 plus 16, 25. R has to be 5. And then alpha has to be arctan of a over b, so of 3 over 4. And so alpha is equal to, punch this into your calculator, arctan of 3 over 4, and this gives us 36 point. Did they specify the degree of accuracy? No, they didn't tell us how many decimal places to use for alpha, so I'll just round off to 1. So I'll say 36.9 degrees. So that means, therefore, the equation they gave us there, there's 3 root 2 sine x plus 45 degrees plus the cos x can be written in the form r cos x minus alpha, and we know r is 5, so 5 cos x and we know our alpha is 36.9 degrees. And that's our final answer for part A. Now part B says, hence solve the equation 3 root 2 sine 3 theta plus 45 degrees plus cos 3 theta is equal to negative 4 for thetas between 0 degrees and 180 degrees. So the hence keyword implies that we must use information from an earlier part to help us solve this. So I hope you can see that there's some similarities between this equation and the equation we're given in part A. Right, in fact, I'll just copy this whole thing. So it's going to be useful. I just want you to compare this and this expression. So I've got 3 root 2 in both of them, sine, but my x appears to have become 3 theta. The 45 degrees is still the same, cos, then my x has become 3 theta. So it looks like they've just used a substitution to say let x equal 3 theta. So if that's true, this must imply then that 3 root sine of 3 theta plus 45 degrees plus cos 3 theta should be equal to 5 cos. We're simply just replacing the x with 3 theta. 3 theta minus 36.9 degrees. And so what that means is I can replace the left-hand side of this equation with just the 5 cos 3 theta minus 36.9 degrees. And our equation that we're solving becomes significantly easier. So I've got 5 cos 3 theta minus 36.9 degrees. And this is equal to negative 4. Okay. And now divide both sides by 5. So I've got cos 3 theta minus 36.9 degrees, and this is equal to negative 4 over 5. Then I get 3 theta minus 36.9 degrees is equal to arc cos of negative 4 over 5. And so the value that we get from punching in arc cos of negative 4 over 5, that is also our principal value, right? So our principal value is going to be arc cos of negative 4 over 5. And don't be tempted to immediately try to solve for theta, so to make theta subject of the formula here. Reason being, we want to find all the other solutions within our interval first, then we'll simplify. Because if you prematurely make theta the subject of the formula, you won't be able to find the other values that are within the given interval. So let's punch arc cos of your negative 4 over 5 into the calculator and see what we get. We are in degrees. So this is arc cos of negative 4 over 5. So this is 143.1301. So this is our principal value, and this is the value we're going to use to look for all our other solutions. So to find solutions, what I like to do is to sketch the graph of whatever function it is I'm solving for. So if it's sine, I draw sine. If it's cos, I draw cos. If it's tan, I do not draw tan.
You just have to say that you're fine when you're not really fine.
I use a formula. So since we're dealing with cos, I know this is a terrible graph, but just bear with me. This is 90 degrees, this is 180, this is 270, 360. So we know our solution here is, it's at 143, so it should be somewhere in between 90 and 180. So I'll put my 143 somewhere here, right? And if I draw a horizontal line, I can see that I've got another solution at this point here. By symmetry, I hope you can see that this here is symmetrical to this here. So this distance is 143. That must mean this distance is also 143. So if I want to know what my value there is, it's just 360 minus 143. So keep in mind that our principal value is in terms of 3 theta minus 36.9 degrees, because I haven't simplified for theta yet. So every solution I'm finding right now is of the form 3 theta minus 36.9 degrees. Okay, and so this is going to be equal to 360 degrees minus 143.1301 degrees. And so 3 theta minus 36.9 degrees is equal to, punch this into the calculator, 360 minus 143.1301, that gives us 0.8699. And I know that at first glance, this value looks like it's clearly outside of our interval. But remember, this interval is for theta. You see that when we then eventually solve for theta in this equation, we're going to end up dividing this by 3. So this 216 that looks too large will eventually shrink so that it actually fits within the interval. And so now the two solutions I'm working with are the principal value and this solution. And I know both of them are in the form 3 theta minus 36.9 degrees. So the first one from the principal value is our 143.1301, and the second one we just evaluated here is the 216.8699. Okay, now let's actually solve for theta. So to solve for theta, we're going to add the 36.9. So 143.1301 plus the 36.9, and then divide by 3. So theta becomes, so that is 143.1301 plus 36.9 divided by 3. That gives us 60.0 degrees, which will be one of our solutions. And here, if we do the same, theta becomes 216.8699 plus the 36.9 degrees, and divide that by 3. You get that theta has to be 84.6 degrees. Those become our two solutions. Okay, we can conclude that therefore theta is either the 60 degrees or the 84.6 degrees. Question number 4. The diagram shows the graph of y is equal to e to the sine 2x cos 4x for x is between 0 and a quarter pi inclusive and its maximum point m. Okay, so that's a key phrase there, maximum point. Find the x coordinate of m. We know we're dealing with a maximum point, so at a maximum point, dy dx is 0. So that means we need to find what dy dx is. And we've got some equation to differentiate. So we've got e to the sine 2x cos 4x. I hope you can see that we essentially have these two functions multiplying, the e to the sine 2x and the cos 4x. So we've got two functions multiplying each other. So I need to differentiate using the product rule. So I'm going to say let u equal the first function, so e to the sine 2x. And then I'm going to say let v equal cos to the 4x. And we need to differentiate. So du dx is equal to, so here be careful because we've got quite a few functions that all need to be differentiated. So you start from outside and you move inwards. So the outside function, that's the exponential. If you differentiate an exponential function, you just get the exponential. So we still have e to the sine 2x. Then move on to the inside function. If you differentiate sine, you're going to get cos. So we've got cos 2x. And then the green function, if you differentiate 2x, you just get a 2. So multiply by 2. So that means our du dx is going to be 2 cos 2x times e to the sine 2x. Right? Now we need dv dx. Here we only have two functions, so start with the outside function. If you differentiate cos, you get negative sine. This is evaluated at 4x. Then move on to the next function, differentiate 4x, you get 4. Okay, and so dv dx is just your negative 4 sine 4x. And now let's find dy dx. So dy dx is going to be, if you look at the MF19, it will say u dv plus v du. So u dv, we're multiplying this and this. So that is negative 4 sine 4x. And this is multiplying your e to the sine 2x plus, then it's v du. So the cos 4x multiplying the 2 cos 2x e to the sine 2x. So I've got cos 4x, and this is multiplying 2 cos 2x e to the sine 2x. I hope you can see that the e to the sine 2x is common in both terms, so I can factor that out. And also I can factor out a 2, so I'll factor out 2e to the sine 2x. In the first term, I remain with negative 2, and this is sine 4x. And then in the second term, taking the e to the sine, I've taken the 2, I should remain with cos 2x, cos 4x. This is our derivative. So we know we're dealing with a maximum point, so we equate out dy dx to 0. So this whole expression is going to be set to 0. So cos 2x, cos 4x, and this is all equal to 0. So at this point I have that either 2e to the sine 2x is 0, or this whole bracket, negative 2 sine 4x plus cos 2x cos 4x is 0. The first equation can't possibly have any solutions because an exponential graph is always above the x-axis and it is never equal to 0. Or another way you can do this is to just take the natural logarithm on both sides, and I hope you can see that you end up just taking ln of 0, which is undefined, so we have no solutions here. And here what we can do is we can use the double angle formula for sine. We know that if we go to the MF19, we get something to the effect of sine 2x is 2 sine x cos x, right? But this is a double angle formula, and the essence of a double angle formula is that the angle on the left is double the angle on the right. So I can manipulate my double angle formula to work with whatever angles I wanted to work with. So if I want a double angle formula for sine 4x, that just means I need to have half the angle on the right. So this has to be 2 sine 2x, and this is cos 2x. So I can replace the sine 4x with my 2 sine 2x cos 2x. So I end up having negative 2, that's in brackets 2 sine 2x cos 2x plus cos 2x cos 4x. This is equal to 0. I hope you can see that I can factor out a cos 2x in both terms. So I end up with cos 2x, and now in the brackets I've got negative 4 sine 2x plus, here it's now just the cos 4x, and this is equal to 0. And here I have either the cos 2x is 0 or the bracket is 0. So the negative 4 sine 2x plus cos 4x is 0. So if we deal with the first equation, we'd get 2x is a cos of 0. So I get 2x is equal to, are we in degrees or radians? We are in radians, so that will be pi over 2. Multiply both sides by 2. Rather, divide both sides by 2, you'd get x is pi over 4. And I hope you can see that pi over 4 would actually be this minimum point of the graph. Because remember, when you do dy dx is 0, you're just solving for stationary points. So it can either be a minimum point or a maximum point. But we found the minimum point. What we want is the maximum point. So this can't be our answer. So we have to try this equation here. So that's negative 4 sine 2x plus cos 4x. To simplify this, we're going to want to use a double angle formula for cos. Reason being, I know if I break this angle down in half, I'm gonna have a 2x. So if I can find a double angle formula for cos that's in terms of sine, my whole equation ends up being in terms of sine, and that's easier for me to work with. So go to the MF19 and you find that there's a double angle formula for cos, but I want the one with sine only, so 1 minus 2 sine squared x. And again, like we mentioned for sine earlier, this is a double angle formula, so the angle on the left is twice the angle on the right, and I can manipulate this to work with whatever angles I want to work with. So I want to break down cos 4x. So that becomes 1 minus, the angle on the right has to be half. So sine squared 2x. Okay, so I replace my cos 4x with 1 minus 2 sine squared 2x. So I end up with negative 4 sine 2x plus 1 minus 2 sine squared 2x, and this is equal to 0. So if we put everything on the right hand side, we've got 2 sine squared 2x plus 4 sine 2x, and then I've got the minus 1, and this is equal to 0. And I hope you can see that what we have here is a quadratic in terms of sine 2x. So let's use the quadratic formula to solve this quadratic equation. So sine 2x is going to be, so a here is the coefficient on sine squared, which is 2, b is the coefficient on sine, which is 4, and c is the constant. So we want minus b plus or minus the square root of b squared minus 4ac divided by 2 times a, and let's punch this into the calculator. So that is negative 4 negative root 4 squared minus 4 times a times c divided by 2 times 2, which is negative 2 negative root 6 over 2. That's one of the solutions. And the other solution is, that's the positive one, that is negative 2 plus root 6 over 2. And let's evaluate this. 2x is equal to arcsine of the negative 2 negative root 6 over 2. Punch this into the calculator. Arcsine of negative 2 negative root 6 over 2. That gives us an error, and that's probably because negative 2 negative root 6 over 2 is approximately negative 2.22. And remember, our sine graph ranges from negative 1 to 1. So if you have any values outside of that range, they're going to give you an error. That's what I should write as no solutions. So that means our solution has to come from this equation. Surely, how many equations have we solved? And we've been concluding no solutions. Okay, so 2x is equal to, that is arcsine of negative 2 plus root 6 over 2. So 2x is equal to, that's arcsine of negative 2 plus root 6 over 2, and this gives 0 0.22668, and then divide this by 2, you should get 0 0.113. Correct to 3 significant figures, which makes sense for the interval that we have. We know that x is between 0 and a quarter pi. If you punch a quarter pi into your calculator, you get that a quarter pi is approximately 0.785. So we've got 0.113, which, I mean, just looking at the diagram kind of makes sense. So that is our answer. Question number 5. The shaded region on the Argand diagram shows points representing complex numbers z defined by 2 inequalities. The shaded region is bounded by a circle and a line parallel to the imaginary axis. The boundaries of the region are included in the shaded region. Part A, find 2 inequalities in terms of z that define the shaded region. Okay, so the circle, we can start with, in fact, I think the line is easier. So we were told the line parallel to the imaginary axis, which is this line here. That's just going to be where the real value is equal to 2, right? But I hope you can see that the shaded region is anything greater than this line, so beyond this line. So we're going to say where the real value is greater or equal to 2. Because if I just say equal to 2, I only mean exactly on that line. But my shaded region also goes beyond that line. So I want the real value greater or equal to 2. But if that was my only inequality, then we're also including all those regions that are outside the circle. So we need to also find the inequality for the circle. So for the circle, your inequality is of this form: z minus whatever your center of the circle is, and it's going to be, in this case, less than or equal to since we want our area to be inside the circle, but we're also including the boundary or the circumference of the circle. If the circumference was dotted, then it would be strictly less than, okay, and then this is whatever the radius is. So we need to know what the coordinates of the center of the circle are. So our center is here. We can tell that it's got a real value of 1 and an imaginary value of negative 2i. So that becomes z minus our 1 minus the 2i. That's our center. And this is less than or equal to the radius. So that's how many units. I can tell here we're moving 1 unit and then 2 units, right? Since it's negative 2 units there. So that must mean our radius is 2. Okay, and so those are the two inequalities that define this Argand diagram. Part B says calculate the least value of argz for points in this region. Okay, so let me erase that and then we can copy our diagram. So remember, argument is the angle formed between the positive real axis and whatever your complex number is. So we're saying what is the smallest angle formed between our positive real axis and any of these points in the shaded region. So it's going to be this here, this point here, that gives us the smallest argument, because remember this time we're on the negative side. So by smallest we mean the most negative. So we need to find that angle there. And to find that angle, we want to use this triangle, right? Because it's a right angle triangle and I know this side has 2 units, but I don't have any other units. Here I can't assume that it's going through the center, and really from our sketch it also doesn't really look like it's going through this. Possibly could be going through the center, but we can't be sure, so we can't use that. I do know that if we just go out of the world of complex numbers for a second and look at the normal coordinate system in real numbers, if I've got a circle, I know it's of the form x minus a squared plus y minus b squared is equal to r squared, right? In our case, we know our center had the coordinates. It was 1 and negative 2i, right? Which in the world of real numbers is just 1 and negative 2. So that would mean we've got x minus 1 squared plus y minus 2, so y plus 2 squared is equal to our radius squared. Our radius was 2, so 2 squared, which is 4. I want us to find the coordinates of this point here. We know that it lies on the circle and we know that it has an x value of 2. So when x is 2, what is y? So 2 minus 1 squared plus y plus 2 squared is equal to 4. So I have 1 plus y plus 2 squared is 4. So I end up with y plus 2 squared is 3. And so if I take the square root on both sides, I get y plus 2 has to be plus or minus the square root of 3. So I get that y has to be negative 2 plus or minus root 3. And here I want you to notice that there's actually 2 points that have an x value of 2. So there's this point up here, and then there's this point we're interested in. So we know that the point we're interested in has a smaller y value or a more negative y value. So for our point, it should be negative 2, negative root 3. So the coordinates of our point there should be, that is, what was the x value? We know the x value or the real value is 2. And then it's going to have negative 2, negative root 3. And you can put I if you want to specify that that is the imaginary part of this point. And the reason why we want the coordinates is because if I know the coordinates of this point, then I can just find the length or the distance from the origin all the way up to this point, which is the hypotenuse of our triangle. And once I have the hypotenuse, I also have the 2 there. So I can use SOHCAHTOA to then find my argument. So you can either just think of this as distance formula, or you can think of this as finding the modulus of your complex number. I'll take it as finding the modulus of my complex number. So let's do that just label this side h for now and say that h is going to be the square root of, so the real part squared plus your imaginary part squared. So our hypotenuse is going to be, we punch that into the calculator. So I just want to simplify this part that's under the square root, because I know if I do the square root of everything, my calculator will just give me a decimal, and I don't want a decimal just yet. So that is 2 squared plus -2, negative root 3 squared. So it means h is the square root of 11 plus 4 root 3. Okay, so now we know the hypotenuse. So what we're looking at is a right angled triangle like this, and we know that we've got some angle theta, which is the argument we're looking for. This side is 2 and this side here is root 11 plus 4 root 3, and we can use SOHCAHTOA to find theta. So what we're saying is we've got the adjacent and the hypotenuse, so we can do cos. So cos of theta has to be equal to our adjacent over our hypotenuse, and so theta has to be arc cos of 2 divided by root 11 plus 4 root 3, and so theta is arc cos of 2 being divided by the root of 11 plus 4 root 3. And I'm just gonna put my calculator in degrees. Here they didn't specify degrees or radians, so it's fine if you give your answer in degrees or in radians since they didn't specify, but I'll give it in degrees. I get 61.8 degrees, so I'll conclude that therefore least value of arc z is 61.8 degrees, and that's our final answer. Question number 6. Solve the quadratic equation 2 plus iw squared plus 4w plus 2 minus I is equal to 0. Give your answers in the form x plus iy, where x and y are real. Okay, so we've got a quadratic equation, but obviously I hope you can tell that this is a complex quadratic equation because we're in the world of complex numbers. So to solve our quadratic equation, we're going to use the quadratic formula. So our a is the coefficient on w squared, so that's 2 plus I. Our b is the coefficient on w, so that's 4. And c is the 2 minus I. And so that becomes w is equal to minus b, so minus 4, plus or minus the square root of your b squared, so 4 squared minus 4a, which is 2 plus I, c, which is 2 minus I. And this is all divided by 2 times a. So 2 times 2 plus I. Okay, so let's simplify this. We can't just punch this into the calculator because your calculator will, well, some calculators can simplify this, but I'd assume the majority of them can't, and sure, working either way. So 4 squared is 16, and then here I've got minus 4, and I hope you can see that I've got a difference of 2 squares. So a difference of 2 squares is anything that can be written as a plus b times a minus b, because I know that I can then simplify this to a squared minus b squared. So in our case, I've got a plus b times a minus b. So my a is 2, my b is I. So that means that just simplifies to 2 squared minus I squared. And this is all being divided by, I won't expand this just yet because I have a feeling that 2 will eventually cancel out with something. So I've got 2 times 2 plus I, and w is negative 4 plus or minus. We continue to simplify. So 16, and then here I've got minus 4. In my brackets I've got 2 squared, which I know is 4, and you should know that I squared is equal to negative 1. So here I've got negative I squared, so that's just 1. So in fact this is 4 plus 1, so I've got negative 4 times 5, which is just negative 20. Okay, so 16 minus 20. And this is all over 2 times 2 plus I. And so what we have is that W is negative 4 plus or minus the square root of 16 minus 20, so of negative 4. And this is being divided by 2 times 2 plus I. Okay, I know that I can rewrite root negative 4 as root negative 1 times 4, right? Because negative 1 times 4 is negative 4. And this then allows me to use this property that says the square root of AB is equal to the square root of A times the square root of B. So in our case, I can say this is the square root of negative 1 times the square root of 4. And I know the square root of negative 1 is I, and I know root 4 is 2. So I end up with 2I for root negative 4. So that becomes W is equal to negative 4 plus or minus 2I. And this is being divided by 2 times 2 plus I. And in the numerator, I can factor out a 2. So I've got 2, and then that becomes negative 2. That's plus or minus. This is now just I, and that's being divided by 2 times 2 plus I. And that 2 cancels out. So you end up with either W is negative 2 negative I over 2 plus I, or W is negative 2 plus I over 2 plus I. Okay. And they specify that they want their answer in the form x plus iy. So we need to simplify this. So this is division of a complex number. So to divide a complex number, you multiply both the numerator and the denominator by the complex conjugate of the denominator. So the complex conjugate of my 2 plus I is 2 minus I. So I multiply my numerator by 2 minus I, and I also multiply my denominator by 2 minus I. So let's simplify. So negative 2 times 2, that's negative 4. Negative 2 times negative I, that's positive 2I. Negative I times 2, that is negative 2I. Then negative I times negative I, that's positive I squared. And this is all being divided by, and then in the denominator, I again have a difference of 2 squares. And I think we did this exact same difference of 2 squares earlier, which was 2 plus I times 2 minus I. And we know that that simplifies to 2 squared minus I squared, which we said is 4 plus 1, which is 5. So I know I just have 5 on my denominator. And so let's simplify. W is equal to, I can see in my numerator, these two cancel out, and I end up with negative 4, and then I know I squared is negative 1, so I've got negative 4, negative 1 over 5, so I've got negative 5 over 5, so I get W is negative 1 as part of my solutions. Let's evaluate the other one. So again, here we're going to multiply by the complex conjugate of the denominator. So in this case, that is the 2 minus I. So 2 plus I multiplied by the 2 minus I. So I get W is equal to, let's expand the numerator. So negative 2 times 2, negative 4, negative 2 times negative I, that's positive 2I. And then I times 2, that's again positive 2I. Then I times negative I, that's negative I squared. And we have the same difference of 2 squares on our denominator, which we know simplifies to 5. So if we simplify our numerator, that is, I've got this negative 4 and I've got negative I squared. I know negative I squared is 1 since I squared is positive 1. So I know here I've got 1 minus 4, which gives me negative 3. And then I've got 2I plus 2I, which is 4I. And this is all being divided by 5. And so that means our solution here is that W is negative 3 over 5 plus 4 over 5I. And these are our two solutions. Number 7, the parametric equations of a curve are x is equal to t squared minus ln 2t plus 1 and y is equal to t over 2t plus 1. Obtain a simplified expression for dy dx in terms of t. So I've got x is equal to t squared minus ln 2t plus 1, and then I've got y is equal to t over 2t plus 1. Okay, so we need to differentiate both these equations separately. So we'll start with the first one. Here it's going to be dx dt. So differentiate the t squared, you get 2t, and then I've got minus, differentiate the ln, so it's 1 over the bracket, so 1 over 2t plus 1, and this is being multiplied by, differentiate the bracket, so differentiate 2t plus 1, you get a 2. Okay, so we have that dx dt is equal to, that is 2t minus 2 over 2t plus 1. Now let's differentiate the second equation. So here we're going to have to use the quotient rule since we've got two functions multiplying each other. So if you go to the MF19, you find that the quotient rule says if you have something of the form y equals u over v, then dy dx would be your v du dx minus u dv dx, and this is all over v squared. So in our case, I'll use the t and I'll use the 2t plus 1. So that means our dy, in this case, be careful, it's not dy dx, it's dy dt. It's going to be, first, we just write down v exactly as it is, so 2t plus 1. Then differentiate u, so if you differentiate t, you're going to get 1, so times 1, minus, then we've got u, so that's the t, and then differentiate v, so differentiate 2t plus 1, you're going to get a 2. And then divide all of this by v squared. So divide by 2t plus 1 squared. So let's do a bit of simplifying on the top. So dy dt is equal to, I've got 2t plus 1 minus 2t. And this is all over my 2t plus 1 squared. And so I get that dy dt is the 2t and the negative 2t cancel out, so I've got 1 over 2t plus 1 squared. Okay, so that's my dy dt, and here we found our dx dt. But remember, what we want is dy dx. So let's create a chain rule for dy dx in terms of dy dt and dx dt. The dy will come from dy dt, and the dx comes from dx dt, but we want the dx on the bottom, so I have to flip this fraction so that it becomes dt dx. And just to make sure you're doing the right thing, the dt's should cancel and give you back dy over dx. So this means that our dy dx is equal to dy dt, which is 1 over the 2t plus 1 squared multiplied by dt dx. So dx dt is the 2t minus 2 over 2t plus 1. So when I flip it, right, I hope you appreciate the fact that all of this is technically being divided by 1. So if I flip dx dt, I also have to flip this side. So I should end up with 1 over that whole thing. So 2t minus the 2 over 2t plus 1. But let's just work on simplifying that on the side. So I've got 1 over 2t minus 2 over 2t plus 1. So what I can do is I'll find a common denominator inside of this denominator here. So I'm just focusing on that part for now. And I want a common denominator for that. So my common denominator will be 2t plus 1. And so now this becomes my 2t being multiplied by the 2t plus 1. Then minus that 2. Minus the 2. And let's simplify this. So that is 1 over, here I've got 2t times 2t, so 4t squared. Then I've got 2t times 1, so I've got 2t, and then I've got my negative 2 there. And this is all being divided by my 2t plus 1. Alright, and this here just becomes, so this 2t plus 1 goes all the way up top. So it becomes 2t plus 1 and it's being divided by 4t squared plus 2t minus 2. So that means if we come back here, this whole thing can be written as this. So let's go ahead and substitute that. So I know my dy dx is going to be my 1 over 2t plus 1 squared multiplied by the 2t plus 1, and this is all over 4t squared plus 2t, and that is minus 2. And here I hope you can see that this 2t plus 1 will cancel out one of the 2t's plus 1 there. So what I end up with is dy dx is equal to, it's 1 over the 2t plus 1 multiply my quadratic 4t squared plus 2t minus 2. Alright, this is dy dx. They did specify that they want a simplified expression for dy dx, so we kind of have to simplify the quadratic, factorize it, and see if this factorizes into something nice. Okay, so again, let's work on that on the side. So I've got 4t squared plus 2t minus 2. Here I can't just divide through by 2. Reason being, I'm not actually trying to solve this quadratic. I just want to simplify it. So instead of dividing by 2, make sure to factor out the 2. Because if you divide by 2, your final answer will end up being wrong because it will be missing that 2 at the end. So this becomes 2t squared plus, that is just t, and that's minus 1. Okay, and I think we should be able to factorize this. Let's see. So I've got 2t, then I should have t here. I'm looking for factors of minus 1. Well, really it's only 1 and 1, and I have to figure out where the negative sign will go. So I want to do 2t times 1 minus 1 times t, because I know 2t minus t should give me a positive t. So that is the factorization of that. If you don't know how to factorize, you can get away with not factorizing. You don't really have to factorize, but don't tell your teachers that I taught you this. So you take your equation, right? And what you're going to do is you're going to use the quadratic formula. So you do the whole shebang. Minus b, so minus 1 plus or minus the square root of 1 squared minus 4ac, and this is divided by 2a. So you're going to get that t, one of them will be a half, and you're going to get one of them is negative a 1. Okay, and to reverse this to the factorized stage, you want to first get rid of your denominator, so it becomes 2t is equal to 1. Then put everything on one side, so you've got 2t minus 1 is equal to 0. That gives you that bracket. And then here it's just moving the negative 1 to the other side. It's equal to 0. That gives you the other bracket. So this is how you can factorize without really factorizing. So yeah, you can thank me later. So that means I can replace my quadratic there with my factorization. So dy dx is equal to 1 over 2t plus 1 multiplied by 2. In fact, I'm just going to put this 2 there, and then I've got 2t minus 1, and then I've got t plus 1. Okay, and this is as simplified as I can get this. I can't simplify further because I've reduced it to all linear factors down here. By the way, if you like the way that I break down questions and you're struggling with your AS or A-level maths, or you just want to make sure that you get the exact grades that you need to get into your dream university, then click the first link in the description down below and I'll help you achieve those dream grades. Question number 8. The variables x and y satisfy the differential equation x squared plus 1 dy dx is equal to kx e to the 2y, where k is a constant. It is given that y is 0 when x is 0 and that y is negative a half when x is 1. Solve the differential equation and find the exact value of y when x is root 3. 8 marks. Nice. Alright, let's see what we're working with. So we've got x squared plus 1 dy dx, and this is equal to kx e to the 2y. Okay, so when you're solving a differential equation, the first step is to separate your variables. So I want everything with x on one side and everything with y on the other side. So I'm going to put everything with y on the left side because I want my dy to stay on top, right? So everything with y will move to the left and everything with x will move to the right. So my e to the 2y will move to the left and it becomes 1 over e to the 2y. My dy remains, and this side I remain with my kx, and now this x squared plus 1 is multiplying this side. When it moves over, it divides. I've got x squared plus 1, and my dx is dividing this side. It moves, it multiplies. Now I have separated my variables, so I have to integrate both sides. So I'm integrating e to the negative 2y dy, and I've just moved that up, right, and changed the power to become negative loss of indices. And then here, so this is gonna be, I'm still pretty convinced that it's called the method of recognition, but I'm not sure what the technical term for this is called, but we'll explain this when we get there. So integrate first your left hand side. This is the integral of e to the negative 2y. So if you integrate an exponential function, it still remains an exponential function. Then hit, or rather differentiate the inner function. If you differentiate the inner function, you get a negative 2. So we have to divide by that negative 2 and add a constant of integration. Okay. What we want to do on the left is use the idea k the integral of f prime of x over f of x with respect to x is equal to k ln f of x. So what this means is that if you differentiate denominator and you find that your first derivative is your numerator, then it simply differentiates to ln f of x. So in our case, we are working with, I've put the k outside, we're working with x squared plus 1. I know if I differentiate x squared plus 1, I'm going to get a 2x. So I need to have a 2 on my numerator here for me to have f of x and then f prime of x on top. But since I didn't originally have this 2, I have to cancel out that 2. So to cancel it out, I just divide by 2 outside of my brackets because this then cancels out and it's as if I changed nothing, right? But what that allows me to do is to say that this just integrates then to k over 2 ln of f of x ln of x squared plus 1. And so that means our result here is just k over 2 ln of x squared plus 1. And this is a solution to our differential equation. Did they ask for us to have this in a specific form? They asked us to evaluate this when x is root 3. Okay, so we might as well make y subject of the formula because it will serve us. So what I'm going to do is, let's do this first. Let's solve for our constants. So we've got c, which is an unknown. We've got k, which is an unknown. But they've given us two sets of coordinates. So we can create two simultaneous equations, right? So we're told when y is 0, my x is 0. So I have this set of coordinates. So I can use that to come up with an equation. So replace y with 0. You end up with e to the 0, which is just 1. So I end up with 1 over negative 2 plus c is equal to, here I end up with 0 plus 1. Remember, ln 1 is 0. So this ends up being 0 because I've got k over 2 times 0. So this gives me that c is 1 over 2. Okay, nice. I have c. Now I can use the other set of coordinates to find k. So we are doing, what are the coordinates? Y is negative a half and x is 1. So I have x is 1 and y is negative a half. Okay. So this becomes e to the negative 2y. So y is negative a half, and this is being divided by negative 2 plus c, which is a half, is equal to k, which is what we're looking for, over 2 ln x squared. What is our x? Our x is 1, so 1 squared plus 1. Okay, so let's simplify. So negative 2 times negative a half, that's just 1. So I've got e to the 1 over negative 2 plus a half, and this is equal to k over 2, that is ln 1 plus 1, so 2. Okay, and multiply through by 2 to get rid of our denominator. So I end up with negative e to the 1 plus 1 is equal to k ln 2. So that must mean my k, I'll write this as 1 minus e. So 1 minus e, and then divide both sides by ln 2. My k is 1 minus e over ln 2. And so if we go back to this here and substitute, I should have e to the negative 2y over negative 2 plus c, which is a half, is equal to k over 2. So that is, my k is 1 minus e over ln 2, and that's being divided by 2, so it just ends up being 2 ln 2, and that's ln x squared plus 1. Okay, and now since we eventually want to find the exact value of y, let's just make y the subject of the formula first before we substitute in our x. Or would that make life easier? I wonder. Root 3 squared, that's just 3 plus 1 ln 4. No, I don't imagine it will be too much of a difference. So let's just make y subject of the formula, and then we'll substitute in at the end. So I'm going to move the half to the other side. So I've got here, I'll stop writing my negative on the bottom and I'll move it in line. So I've got negative e to the 2y over 2, and this is equal to, that becomes 1 minus e over 2 ln 2, and it's multiplying the ln x squared plus 1. And then I've got minus a half. Right, I want to get rid of my denominator here, so I'm going to multiply through by negative 2. So I end up with e to the negative 2y is equal to, the 2 will cancel out this 2 that we have here, then it becomes negative. So I've got negative 1 minus e, and this is over ln 2, that 2 is now gone, remember, ln x squared plus 1, and then I'm multiplying minus a half by minus 2, so it becomes positive 1. Okay, so I've got e to the negative 2y is equal to, if we expand this, I end up getting positive e minus 1 over ln 2, and that is ln x squared plus 1 plus 1. And now I'm going to take ln on both sides so that I end up with negative 2y, and this is ln of this whole thing. So e minus 1 ln 2 ln x squared plus 1 plus 1, and multiply both sides by negative a half to get rid of this negative 2. So I get y is negative a half ln e minus 1 over ln 2 ln x squared plus 1 plus 1. And then we were told to evaluate this at x is root 3. So let's do that. So at x is root 3, I have that y is negative a half ln e minus 1 over ln 2 ln, this becomes root 3 squared plus 1 plus 1. Okay, and so y is equal to negative a half ln e minus 1 over ln 2 ln of root 3 squared is just 3. 3 plus 1 is 4 plus 1. And let me close my brackets. Now I'm pretty sure I can simplify ln 4 over ln 2. Reason being, I can write ln 4 in terms of ln 2. So ln 4, if I want to write this 4 in terms of 2, I know that that is ln 2 squared, because 2 squared is 4. And then this allows me to bring down the power, because I know there's a law of logarithms that says ln a to the n is n ln a. So I know that I can write this as 2 ln 2, right, which would allow me to cancel out the ln 2's. So what we're saying is that this here becomes negative 1 over 2 ln e minus 1 over ln 2 multiplied by 2 ln 2 plus the 1, okay, and we know our ln 2's cancel out there, and so I've got y is equal to negative a half ln, and then I've got 2 multiplying the numerators there, so 2e minus 2, and then I've got my plus 1 there, no pun intended, minus a half ln 2e minus 2 plus 1, that's minus 1, okay, and we can conclude that therefore at x is equal to root 3, the exact value of y is negative a half ln 2e minus 1, and that is the final answer. Question number 9, part A. By sketching a suitable pair of graphs, show that the equation sec 2x is equal to negative e to the x has only one root in the interval x is between 0 and half pi. So I saw a fancy solution where you can take this sec 2x, right, and write it as 1 over cos 2x, and this is equal to negative e to the x. Okay, and now what you can do is multiply both sides by cos 2x, so you get 1 is equal to your negative e to the x cos 2x, and then divide both sides by the negative e to the x. So I've got negative 1 over e to the x is equal to cos 2x, and here what you're going to do, I know I can rewrite that as negative e to the negative x using laws of indices, and that's just cos 2x. So that instead of drawing the graph of sec 2x, I'm just going to draw the graph of cos 2x, which is pretty cool. But what I would typically do is to just sketch the graph of sec 2x, but I think we can all agree that it's easier to sketch the graph of cos 2x. So in this case, yeah, let's do that. And if you ever come across a situation like this, and it is a situation where you can manipulate and still end up with two nice graphs, then do that. Otherwise, don't. It's not every day you can do this manipulation and get away with it, so why not? And to be fair, they didn't specify which graphs, they just said a suitable pair, so don't worry about it. So let's draw our plane. So I've got a y-axis, I've got an x-axis, and I know we are going up to 1 over 2 pi. I think let's start with, which graph should we start with? So the two graphs we're going to sketch are y is equal to negative e to the negative x and y is equal to cosine of 2x. Right. We can start with the exponential one. So I hope that you know what the graph of an exponential function looks like, at least what the graph of y equals e to the x looks like. So I know y is equal to e to the x looks like this. This is y is equal to e to the x. I can see there's a negative x there. That negative x tells me that there has been a reflection in the y-axis. So it means now my graph is actually looking like this instead, right? This is now y is equal to e to the negative x. However, I also have a negative here, which tells me that my graph has actually then been reflected in the y-axis as well. So it means my final graph actually looks like this. This is my y is equal to e to the negative x. Okay, so the green part, negative 1, is going to cross your y-axis at negative 1 because your original y equals e to the x crosses the y-axis here at 1, and so this red one also crosses at 1, even though it's slightly off. So let's shift it so it looks like it's crossing at 1, and the green one is just a reflection of the red one. So if the red one crosses at +1, the green one should cross at -1. So I know I've got something like that. Okay, and label your graph. This is y is -e to the -x. Now we want the cosine graph. I hope you know what the cosine graph looks like. So I know a standard cosine graph, y equals cos x, will look like this, right? And this is going all the way up to 2 pi. That will be 3 pi over 2, and that will be pi. This would be pi over 2. However, this 2 tells us the number of complete cycles between 0 and 2 pi. So it's telling us that our graph has been shrunk, and it actually now completes its first cycle at pi, and then by the time it hits 2 pi, it has completed 2 full cycles. Okay, so now I know it's gonna hit instead of hitting my x-axis at pi over 2, it's going to hit it at pi over 4, which is half of that, and then it hits its minimum there, and then somewhere in between here it's going to hit this, and then it comes back to the top. So we're looking at something like this, right? And then if you were to continue, it should be, you should have that, so that you've got your 2 complete cycles. But remember, our graph sketch is only going up to 1 over 2 pi or pi over 2. So really, I just want this first bit. That's what I'm looking at. So if I can label pi over 4 to be somewhere there, I know that what I want is we start at 1. So 1, and I know I'm going to end at -1. So I'm going to have that, and then that. And so we're looking at something like, that's a bad curve. That's better. Something like this. And this would be my y is equal to cosine of 2x. And remember, the point here is to prove that we only have one root in this interval. And the root is your point of intersection. So circle where you're going to have that point of intersection. That represents your one root. And that's going to be our final answer. Part B says, show by calculation that this root lies between 0.9 and 1. Okay, so we can take the equation we're given in part A, which is that sec2x is equal to -e to the x. So what we want to do is to create a function f of x, and this function is just going to be the result of putting all the terms we have in this equation on one side. So it's just sec2x plus e to the x. Okay, and we want to evaluate this function at 0.9 and at 1. And if we have a sign change, then our root does indeed lie between those two values. So this is sec of 2 times your 0.9 plus e to the 0.9. So let's punch this into the calculator. Firstly, make sure you are in radians. And then if your calculator doesn't have sec, you can punch this in as 1 over cos, because sec is 1 over cos. So 1 over cos 2 times your 0.9 plus your e to the 0.9, and this gives us a negative 1.942. And now let's do f of 1. This is sec of 2 times 1 plus e to the 1, which is 1 over cos of your 2 times 1 plus e to the 1. And this does give us a positive value, so we did get that sign change we're looking for. And make sure to always conclude for this question, because the second mark is in the conclusion. So you can say, therefore, since there is a change in sign, this root lies between our 0.9 and 1. Okay? And that is the final answer. But see, if you've never seen this question before, it probably, the English probably doesn't make sense. But show that if a sequence of values given by the iterative formula xn plus 1 is equal to half a cos of negative e to the negative xn converges, then it converges to the root of the equation in part A. Okay, so what they're saying is that if we take this iterative formula and we carry out our iterations and we get an answer from this iterative formula, does this mean that the answer we get from this iterative formula is the same as the answer to this equation in part A? And it can only be the same as the answer of the equation in part A if if this iterative formula is just a different way of writing the equation in part A. So what we have to prove is that this equation is just a different way of expressing the equation in part A. So let's do that. So remove the n plus 1s and the n's. X is equal to a half arc cos of negative e to the negative x. And we are trying to prove, what did we have? Sec 2x is equal to negative e to the x, right? Yeah. Maybe just to make life easier, since they've given us something in arc cos, I will probably get to cos before I get to sec first. So I can express this instead of sec 2x, I can express this as 1 over cos 2x is equal to negative e to the x. And so I know the target I'm aiming for is to get something in the form 1 over cos 2x. So what we can do is, clearly we've got arc cos, so we eventually want to make this into just normal cos without the minus 1. So multiply both sides by 2 and you get 2x is equal to your arc cos of negative e to the negative x, and then apply cos on both sides. So we want to do cos of 2x is equal to cos of the arc cos of negative e to the negative x, because I know that cos and arc cos cancel out, and so I just end up with cos 2x is equal to negative e to the negative x. And I hope you can see that we're almost where we want to be. So I know that using laws of indices, in fact we did this manipulation earlier up there. I know that using laws of indices, this here is the same as that. So I can write that as my negative 1 over e to the x. So this is negative 1 over e to the x. And so now I can multiply both sides by e to the x. So I've got e to the x cos 2x is negative 1. And if you divide both sides by cos 2x, you get e to the x is negative 1 over cos 2x. And now just multiply both sides by negative 1, and you end up with your 1 over cos 2x is equal to negative e to the x, and 1 over cos 2x is sec 2x, which is negative e to the x. Okay, and that would be our final answer. Part D. Use the iterative formula given in Part C to calculate x, correct to 3 decimal places. Give the result of each iteration to 5 decimal places. Okay, so the iterative formula we had in Part C was this one. Okay, so I'll just copy this because that is essentially our iterative formula, except it's just missing the ends. So this is n plus 1 and that there is n. Okay, so we need to pick a starting value, an initial value, so x0 for iterations, and we can pick any value. In part B, we deduce that our root must be between 0.9 and 1, so we can pick any value within 0.9 and 1. So I'm just going to use the 1 because it's easy to work with. So I'll say x0 is 1, and so x1 is going to be a half arc cos of negative e to the negative 1. Okay, so let's punch this into the calculator. This is 1 over 2 arc cos of negative e to the negative 1, and that gives us 0.9737. They want each iteration to 5 dp. So 9737, I need one more decimal place, 6. Okay, and then let's go on to x2. Now for x2, what I want you to do is I want you to replace our initial value or x0 there with the ANS button. So on your calculator, you'll find a button written ANS. It stores the result of your previous answer. And in this case, that's going to be the result of your previous iteration. Okay, once you've done that, well, let me do that first. Once you've done that, press equals, and you should get the next result. That is 0.97903, correct to 5 decimal places. Okay, we keep going. So now don't change anything on your calculator, simply press the equal sign. And you're going to get a 0.97796. Okay, we still have to keep going, we're not yet there. So press equals again, and it's 0.97818. It looks like it has converged. So this is 0.978 to 3 decimal places, and this is also 0.978 to 3 decimal places. Perfect. So therefore we can conclude that x is 0.978, and that's our final answer. Question number 10. Let f of x equal x cubed plus 2x minus 11 divided by 3 plus x times 2 plus x squared. Part A, express f of x in partial fractions. So when you are dealing with partial fractions, the first step is check whether you're dealing with an improper fraction or a proper fraction. So an improper fraction is a fraction in which the highest power in the numerator is either equal to or greater than the highest power in the denominator. So in our case, if you expand your denominator, you find that it's going to be an improper fraction. So let's do that. That's your x cubed plus 2x minus 11, and it is being divided by, that is 3 times 2, which is your 6, 3 times x squared, 3x squared, then we've got x times 2, so plus 2x, and then x times x squared, which is your x cubed. And if we just rearrange this, I hope you can see we've got x cubed plus 2x minus 11 being divided by x cubed plus 3x squared plus 2x plus 6. And here the highest power in the numerator is equal to the highest power in the denominator. So we do have an improper fraction. And if you do have an improper fraction, what you want to do is you want to first find a constant, right? We need to get a constant which will help us make this proper. So you can do it one of two ways, either by polynomial division, or you can re-express your numerator in terms of your denominator and then manipulate it to then get your constant. I prefer the second method, which is what we're going to do in this case. So what you're going to do is just copy the whole denominator onto the numerator. Right, and we still have our denominator here, which is our x cubed plus 3x squared plus 2x plus 6. And what we want to do is we want to get the original numerator that we had. So I can see that the x cubed will go term by term. I can see the x cubed that we had in the numerator is fine, but originally we didn't have a 3x squared. So I have to subtract 3x squared outside. I can see that the 2x that we had is here, so that's fine. But now instead of having negative 11, we have 6. So what should we add to 6 to get our negative 11? So that has to be, if you do the maths, that's negative 11, negative 6, so x has to be negative 17. So that means outside the bracket, I should have a negative 17, because I know if I do 6 minus 17, it gives me back my negative 11. And so what this allows us to do is to say, I can distribute my denominator, and so I have this whole bracket, which is your x cubed plus 3x squared plus 2x plus 6, that is being divided by a denominator because we want to distribute the denominator. And now I have the rest of this here, which is our plus negative 3x squared, negative 17, and that's being divided by our denominator, our x cubed, plus 3x squared, plus 2x plus 6. And I hope you can see that in the first term, this just cancels out, and that gives us 1. So I've got 1 plus my negative 3x squared, negative 17, which is all being divided by x cubed plus 3x squared plus 2x plus 6. And so now this has become a proper fraction, and we can carry out or decompose this into partial fractions. So let's do that. So I've got negative 3x squared, negative 17, and that's being divided by, now I no longer want the expanded version of my denominator, but rather I want the factorized version. So I'll take the 3 plus x times 2 plus x squared. So 3 plus x times 2 plus x squared. And at the end, don't forget the constant. It will be part of our solution. So here the 3 plus x is a linear factor, so I have a over 3 plus x. And the 2 plus x squared is a quadratic vector, so I'm going to have bx plus c over my 2 plus x squared. Now multiply through by 3 plus x and 2 plus x squared to get rid of all your denominators. So I've got negative 3x squared, negative 17 is equal to a times your 2 plus x squared. And this is adding to the bx plus c, which is multiplying your 3 plus x. Okay. And now we're going to say let x equal negative 3, because I know if I use negative 3, this bracket here is going to be 0, and it's multiplying this bracket. So overall, the second term becomes 0, and it allows us to evaluate a. So that becomes negative 3 times negative 3 squared minus 17 is equal to a times 2 plus negative 3 squared. And again, the second term is 0, so you can ignore that. So we've got negative 3 squared, which is 9 times your negative 3, that's negative 27, and negative 17, that's negative 44. And this is equal to, we've got 3 squared, which is 9, plus 2, 11, so 11a. Divide both sides by 11, you get that a has to be negative 4. And now we need to find either b or c. Since we know what a is, we can do let x equal 0, with the idea being I will have 0 multiplied by b, so this part falls away, and it allows me to evaluate c because I already know what a is. So that ends up being negative 3 multiplied by 0 squared minus 17 is equal to our a, which is negative 4, times, so that's 2 plus 0, so just times 2, plus the b falls away, so I've got c multiplying 3 plus 0, so 3. And so here I just have negative 17 is equal to negative 8 plus 3c. And so I've got 3c has to be negative 17 plus 8, which is negative 9. So divide both sides by 3. C has to be negative 3. Now we need to find b. For b, we can use x as 1. So let x equal 1. And now we're just substituting in. So it becomes negative 3 times 1 squared minus 17 is equal to our a, which is negative 4 times 2 plus 1 squared, plus b times 1 plus c, which is negative 3. So negative 3 times 3 plus 1, so that's 4. I've got negative 3, negative 17, that's negative 20. And this is equal to 2 plus 1, 3 times negative 4, negative 12. Then here I have 4b minus 12. And that's negative 20 is equal to negative 24 plus 4b. And so I get that 4b is equal to 24 minus 20, which is 4. So b has to be 1. So let's put everything together. I know that the decomposition of this bit, right, is going to be, it is a over 3 plus x. So a is negative 4 over 3 plus x plus bx plus c. So x, because our b is 1, plus c, so minus 3 over the x, 2 plus x squared. 2 plus x squared. But remember, what we were interested in was the full decomposition of f of x. So we need to then bring back this constant, because what we found here was the decomposition of this part. So it's 1 plus whatever we got for the decomposition of this. So it becomes 1 minus 4 over 3 plus x plus your x minus 3 over 2 plus x squared. And that is the final answer. Part B says, hence obtain the expansion of f of x in ascending powers of x up to and including the term in x squared. Okay, so we can use this here, right, because we know that this is f of x. And we're going to move all the denominators up to the numerator. So I can rewrite my f of x as being 1 minus the 4 times 3 plus x. Using laws of indices, this becomes negative 1, and this becomes x minus 3 times your 2 plus x squared, and again becomes negative 1. So let's go it term by term. Let's expand this part first. So that's your negative 4, 3 plus x to the negative 1. The formula we want to use to expand this requires this first term here to be a 1. So we're going to need to factor out that 3. So negative 4, and then I'll factor out 3. I've got 1 plus x over 3. And this is to the negative 1. Now distribute that negative 1. So it becomes 3 to the negative 1 and the bracket to the negative 1. Okay, and so outside I end up with negative. This is 4 over 3 times your 1 plus x over 3 to the negative 1. And now that this first bit is 1, I can use my binomial expansion formula. So that's going to be negative 4 thirds, and that is 1 plus nx. My n is negative 1, my x is x over 3, plus n minus 1, and this is over 2 factorial, times our x squared, so our x is x over 3. And they said up to and including the term in x squared. Okay, so let's simplify this. So I've got negative 4 thirds, and I've got 1 minus x over 3, and then let's simplify the coefficient on x squared there. So it's going to be negative 1 times negative 1, being divided by 2 factorial, and this is multiplied by, keep in mind that here on the x over 3, when I expand this, it's x squared over 3 squared. So I'm going to get a 3 squared on the numerator, on the cut, so I'm going to get a 3 squared on the denominator. So I'm going to end up having 1 over 9 that I'm multiplying by here. So 1 over 9, and so that means this whole thing becomes 1 over 9x squared. Okay, and so that means the expansion of negative 4 thirds times 1 plus x cubed to the negative 1 is going to be negative 4 thirds plus 4 over 9x minus 4 over 27 x squared. Okay, so that's that bit. Now for this part here, what we have to do is we first have to expand the 2 plus x squared to the negative 1. Then once we expand it, we then multiply by the x minus 3 bracket. Okay, so let's do that on the side. So I want to do the expansion of 2 plus x squared to the negative 1. Again, the binomial expansion formula requires this first part to be a 1, so we need to factor out that 2. So I'm going to have 2 and then 1 plus x squared over 2, and that's to the negative 1. Distribute the power, you get 2 to the negative 1, and then you've got the bracket being to the negative 1. And so 2 to the negative 1 is 1 over 2, and this is multiplying 1 plus x squared over 2 to the negative 1, and we can expand. So this is 1 over 2, and it's n, so it's 1 plus n x. In this case, our x is x squared over 2, and then it's going to be plus n minus 1 over 2 factorial times our x. Now that I think about it, this third term isn't necessary because we end up having x squared over 2 squared, and when we'd eventually simplify this, this would give us x to the 4. But remember, we were told to expand up to x squared only, so I don't actually need that part. So I can erase that, and so this really is all I'm expanding here. So that becomes a half, and this is 1 minus x squared over 2. And if you expand this, we're saying that half of 1 plus x squared over 2 to the negative 1 is half times 1, that's a half. Then I've got half times negative x squared over 2, that's negative x squared over 4. So that part is simply the expansion of 2 plus x squared to the negative 1. But remember, this has to be multiplied by x minus 3. So we have to do x minus 3 multiplied by half minus x squared, not x to the 4, but x squared over 4. And let us expand this. In fact, I think I might just rewrite this. Instead of x minus 3, I want minus 3 plus x. That's really just preference because I want to start by multiplying with the number first and not the variable. So negative 3 times a half, I get negative 3 over 2. Then I've got negative 3 times the x squared over 4, that becomes positive 3 over 4x squared. And then I've got the x times the half, that gives me a half x. If I do x times negative x squared over 4, I get a term in x cubed, which I don't want. Yeah. So now this here that we have, that's the expansion of x plus 3 multiplied by the 2 plus x squared to the negative 1. So we can put everything together since we have all the expansions. We now know that f of x is equal to the 1 that we had there. And then remember, I took the minus with me when I was expanding, so don't then subtract again. So our expansion here was this, negative 4 thirds plus 4 over 9x minus 4 over 27x squared. And then we have to add the green expansion, which is this result there. So that becomes negative 3 over 2 plus 3 over 4x squared plus the half x. And now let's simplify like terms. So we've got, for the terms independent of x, 1 minus 4 thirds, which is minus a third. And then we've got minus a third minus 3 over 2. I'm not doing that in my head. Minus a third minus 3 over 2. That is negative 11 over 6. So negative 11 over 6. And then for the terms in x, I've got 4 over 9 plus a half. So 4 over 9 plus a half, that is 17 over 18 x. And then for the terms in x squared, I've got negative 4 over 27 plus 3 over 4. Negative 4 over 27 plus 3 over 4, which is, that's a hell of a fraction, 65 over 108 x squared. Alright, and this is the expansion of f of x up to and including the term in x squared. Question number 11. With respect to the origin, or the points A, B, C, and D have position vectors given by OA 153, OB 041, OC 1 negative 3 1, and OD 3 negative 5 4. The line M passes through points A and B. Part A, find a vector equation for M. So vector equation is of the form R is equal to A plus lambda B, where A is the position vector of a point on the line, so it can either be OA or OB, and B is the direction vector of the line. So since our line is going through the points A and B, our direction can be AB. You could also use BA if you want. It's the same, or it's not the same thing, but it still works. Okay, so let's find AB. That's going to be OB minus OA. So OB is 041 minus our OA is 153. And so that's 0 minus 1, which is minus 1, 4 minus 5, which is minus 1, 1 minus 3, which is minus 2. So our direction is minus 1, minus 1, minus 2. So we can conclude that therefore R, the equation for M is R is equal to our point. You can use OA or OB. I'll use OB because it's simpler. So 041 plus lambda, and our direction is -1, -1, -2, and that's our final answer for A. Now in part B, they want us to find the position vector of the point of intersection of M and the line passing through the points C and D. Okay, so we already know the equation of M to be R is equal to 041 plus lambda times -1, -1, -2. We need to find the equation for the line passing through C and D. So I define that as line L. So let L be line passing through C and D, and we need to find its vector equation. So the procedure is the same as we did in part A. We need to find a direction. So our direction will be CD since it's passing through the points C and D. So to get that, it's OD minus OC, and OD is going to be, we were given to be 3 negative 5 4 minus OC. So OC we were given to be 1 negative 3 1. So this becomes 3 minus 1, which is 2. Then minus 5 minus minus 3, so minus 5 plus 3, which is minus 2. Then 4 minus 1, which is 3. Okay, so this here is the direction for the line CD. So you can say our line L as the equation R is equal to, that's going to be, we can pick any point, so either C or D. I'll use C, which is the 1 negative 3 1, plus, this time let's use mu because we've already used lambda, and that's 2 negative 2 3. Okay, and we said our other equation was M, and we want to find where these two equations intersect. So what we can do is write these in their parametric form, which is to say my x component here comes from saying 1 plus mu times 2, so 1 plus 2 mu. My y component comes from saying negative 3 plus mu times negative 2, so negative 3, negative 2 mu. And my z component comes from saying 1 plus mu times 3, so 1 plus 3 mu. And we'll do the same here. My x component comes from 0 plus lambda times -1, so negative lambda. My y component comes from saying 4 plus lambda times -1, so 4 minus lambda. And then my z component comes from saying 1 plus lambda times -2, which is 1 minus 2 lambda. Okay, and since we're solving for a point of intersection, we simply have to equate our equations together to find that point of intersection. So 1 plus 2 mu is equal to negative lambda. That's equation 1. Our second equation is negative 3 negative 2 mu is equal to 4 minus lambda. That's equation 2. and 1 plus 3 mu is equal to 1 minus 2 lambda. That's equation 3. So our goal here is, if we know what either lambda or mu is, we can then find what the point of intersection is, because this gives us the coordinates of any point that lies on line L. What differentiates each point is just its value of mu. So we just need to find either the exact value of mu at our point of intersection or the exact value of lambda. So we can do that by solving simultaneously. So using equation 1, I can make lambda subject of the formula by multiplying through by -1, get lambda is -1, -2 mu, and I can use equation 2 to then substitute in my lambda. So I get -3, -2 mu is equal to 4 minus lambda. So that's 4 minus -1 minus 2 mu. And if we simplify, I've got -3, -2 mu is equal to 4 minus -1, so plus 1, minus 2 mu, so plus 2 mu. Okay, so that's -3, -2 mu is equal to 5 plus 2 mu. And so if I move the -2 mu to that side, it adds to the 2 mu, and you've got 4 mu. And then I've got -3, -5, so I've got -8. Divide both sides by 4, you get that mu is -2. And so now I know at my point of intersection, mu is -2, so I can simply substitute into this and get my x, my y, and my z. Okay, so that's going to be, I've got x is going to be 1 plus 2 times mu, so that's 1 minus 4, which is -3. Then my y is going to be -3, -2 times -2, which is 4 minus 3, so that's going to be 1. And my z is going to be 1 plus 3 times -2, which is -6 plus 1, so -5. And so therefore, my point of intersection is going to have the position vector -3, 1, and -5. And that's going to be our final answer for B. Now part C says, find the position vector of the foot of the perpendicular from C to M. So let's sketch this out. We've got our line M, right? This is not an accurate sketch, it's just for us to get a picture of what's going on. And we've got a perpendicular. This perpendicular is from C, and it touches M at the foot. So I'm going to label this the point X. So we are required to find the position vector of the foot. So we're required to find what OX is. So the idea we want to use here is that I know that the dot product of two vectors that are perpendicular is equal to 0. So in our case, I'm going to dot Cx with the direction of M, and that's going to be equal to 0 since M is perpendicular to Cx. Okay, but for me to be able to find Cx, I need to know what Ox is. So X lies on the line M, so I can get the general coordinates of any point that lies on line M using its equation. So the equation for line M is here, right? And we can write it in what's called the component form, which is similar to the parametric form we used above. But this says that our x is going to come from 0 plus lambda times -1, so that's just negative lambda. Our y is going to come from 4 plus lambda times -1, so 4 minus lambda. And our z comes from 1 plus lambda times -2, so 1 minus 2 lambda. Okay. And so these are the general coordinates of any point that lies on line M. The only thing that differentiates the points is just the value of lambda. Okay, so I can say that OX, since it lies on line M, must have the general coordinates negative lambda, 4 minus lambda, 1 minus 2 lambda. So since I want to find CX, that's going to be OX minus OC. So OX we know to be negative lambda, 4 minus lambda, 1 minus 2 lambda, minus our OC, which we were given in the stem of the question to be 1, negative 3, 1. 1, negative 3, 1. Okay. And so CX is going to be, let's subtract, so negative lambda, negative 1, and then 4 minus lambda minus 3, so that's plus 3. So 4 plus 3 is 7, so 7 minus lambda, then 1 minus 2 lambda minus 1. The 1 and the minus 1 cancel out, so I end up with minus 2 lambda. This is my CX. And we said we want to dot CX with the direction of M. So I'm going to do CX dot the direction of M. Since these two are perpendicular, this is going to be 0. So my CX is the negative lambda, negative 1, 7 minus lambda, negative 2 lambda, dot the direction of M. So we know M has the direction negative 1, negative 1, negative 2. So that is negative 1, negative 1, negative 2. And this is equal to 0. So now we multiply. So it's negative lambda, negative 1 times negative 1. So negative lambda, negative 1 times negative 1 plus negative 1 multiplying the 7 minus lambda. And then the negative 2 lambda times the negative 2. And let's simplify. So negative 1 times negative lambda, positive lambda, negative 1 times negative 1, positive 1. Then negative 1 times 7, that is negative 7. Negative 1 times negative lambda, positive lambda. Then I've got negative 2 lambda times negative 2, that's positive 4 lambda. And this is equal to 0. Simplify like terms. Lambda plus lambda, that's 2 lambda, plus 4 lambda, that's 6 lambda. 6 lambda. And then I've got 1 minus 7, that's going to be minus 6 is equal to 0. So 6 lambda is equal to 6. Divide both sides by 6, you get that lambda has to be 1. Okay, so we now know that at the foot of the perpendicular, our lambda is 1. So since we know the general coordinates of OX are this, we can simply substitute in lambda to get our exact coordinates. So let's do that. So OX is going to be, this is negative 1, 4 minus 1, 1 minus 2 times 1. And so therefore OX has to be, this is negative 1, 3, then 1 minus 2, which is negative 1. And this is the position vector of the foot of the perpendicular from C to M. Okay. That also happens to be the last question on this paper. I hope you found this breakdown useful. If you did, please leave a like and subscribe, and share this video with all your friends who are doing AS or A-level maths. And by the way, if you're struggling with AS or A-level maths, click the first link in the description down below to book a free discovery call with me, and I'll help you get your dream grades.